Hey, pre-calculus, welcome to our lesson for the day. So we're starting off with a warm-up. Normally you'd be doing this on paper in class, but circumstances prevent that, obviously. So we're going to find the component form of the vector called v, represented by this ray pq, where p is at the coordinates -3, 4, q is at the coordinates -5, 3. So I'm going to go ahead and graph p first, -3, 4. Right, so that is point P, and Q is at -5, 1, right here. There's Q. So I'm going to draw a ray from P to Q. All right, yay. We're supposed to find the component form. All right, well, so to find the component form, I need to know how far sideways in the X direction I have gone and how far vertically in the Y direction I have gone. I'm going to use pointy brackets for component form. I'm just going to count squares now that I have my little triangle drawn. So I went in the X direction first, -2, and in the Y direction was -3. All right, well, there's my component form. Let's see what's next. So today we're going to look at vectors. We have 2 learning targets. I'm going to postpone this one. Actually, we'll get to this one tomorrow or Monday, I guess. So the learning target for today is you'll be able to find the magnitude of a vector. And so we remember, hopefully, from yesterday, from the definition of what a vector is. Vector is a quantity that can be described with both direction and magnitude. And so we know magnitude means like the size, the length of the arrow that is drawn. Um, so just let's go back to this problem from the warm-up. We had drawn a nicer drawing because I drew this one ahead of time. But we'd drawn a vector from P to Q. We found in this case, the vertical and then the horizontal. This is my triangle is drawn differently. It's the same components whether I put them above that vector or below. So I've got a little right triangle, right? So in order to find the length of this ray, P to Q, it's really just the length of the hypotenuse. I've got a right triangle. I know this size of the legs. We can count the squares. We'd already done that. So the length is 3. Lengths always have to be positive numbers. So the component forms, we had the x component was negative and the y component was negative. But if we're thinking about just lengths, length has to be a positive number. It's a distance. So I've got the legs, 2 and 3. And in order to find the length of the hypotenuse, you guys remember how to find the length of a hypotenuse in a right triangle? I knew it. Okay, so we're going to do a squared plus b squared plus equals c squared. And so we've got the 2 legs, so I'm going to do 2 squared plus 3 squared. And that is going to equal c squared. A little bit more workspace. So this is 4. I guess we'll just go in blue. This is 9. 4 plus 9 is 13. And I do not want c squared, so one more step, I need to do the square root. And I'm going to stop right there. I know your geometry teacher probably told you this. We're going to leave that in radical form. There are certainly occasions where we would want to find what is the square root of 13 and get a decimal approximation for that. This is not one of those times. So it's going to leave it in radical form and say that the length of the hypotenuse is the square root of 13, or radical 13. That is the length of ray PQ. Okay, well, that's basically what you need to know about finding the magnitude of a vector. However, I'm going to have you write down these 2 formulas. I mean, conceptually, that's the idea, but here are 2 formulas we can use to find the magnitude. So let's start up here at the top. Let's not get ahead of ourselves. Vector magnitude has a special notation in math. It looks just like absolute value, which I don't know whose idea it was to come up with a new idea and use an old symbol that we've already got. Absolute value, and they said, well, we'll just put absolute value symbol on a vector, and that will mean magnitude. Well, it's not anywhere related to absolute value. So it actually is not absolute value. It happens to be the same looking symbol. Sometimes, to avoid that confusion, sometimes we'll use double bars. There's no difference in what it means. It's just whether this publisher put single lines and that publisher put double lines and which textbook we're looking at. It means the same thing. So that is the notation for magnitude of a vector. And magnitude just means the length of the hypotenuse if you draw your little component vectors to get your right triangle. So we can use the distance formula if we have coordinates of the initial point and coordinates of the terminal point, like we did in the warm-up problem. In that do now, we were given coordinates, so we could just plug the coordinates in. This is just the distance formula, and just instead of d for distance, it's been relabeled as the vector magnitude over here. So subtract the two x coordinates, square that difference, and then add it to you do the same thing with the y coordinates. Subtract the y coordinates, square that difference. You add those two together, and then square the whole thing will give you the magnitude. Or if we are given component form rather than coordinates of the initial and terminal point, if we have the coordinates, if we have the components, then basically we're ready to just do a squared plus b squared equals c squared. So this is the Pythagorean theorem. It's been solved for c, so we don't have to repeat those algebra steps every time. So the magnitude of the vector is the square root of a squared plus b squared, where a is one of the components, b is the other component. Technically, it doesn't matter which one is x and y, because when you square them and add them, it doesn't make any difference. Okay, so let's look at one example. Here's a vector that is given to us in component form. So it's got components -3 and -7. We're going to find the magnitude of this vector. I'll just name it v. And so this is going to be -3 squared plus -7 squared. The negatives are not really going to make any difference because when I square it, that negative is going to go away. So it's going to be 9. That's going to be 49. So I'm going to add together 9 and 49, which would be square root of 58. And we always want to double check, can I simplify this radical? So I got to think, what could multiply into 58? 2. That's not going to help me simplify. It was 4 going to go into that. 25. No, it's 20. No, it says prime. 2 times 29. So that's those are primes. So this cannot be simplified. So radical 58 is my magnitude. Let's look at a second example. So here's the same formulas again, but this time let's do an example where we're given coordinates. Okay, so in order to do the magnitude of this vector, it's represented by this ray PQ, where P is the initial point. We know that from its location in the ray notation, initial point P, terminal point Q. So make sure we can see this formula. So it's going to subtract the x coordinates, subtract the y coordinates, square them, add, just like the formula shows. Okay, so x coordinate of -3, the other x coordinate is -5. I'm subtracting those. We can't forget when we're subtracting a negative number, essentially this subtraction and that negative basically combine to make it an addition problem. And add that plus. Okay, so I'm going to do the subtraction of the y coordinates over here. So 4 minus 1. Okay, goodbye formula. I'm going to scroll down so you have some extra workspace. Okay, so -3 plus 5, that's 2. And 4 minus 1 is 3. 2 squared is 4. 3 squared is 9. Add those together, square root of 13. Okay, I know 13 is a prime number, so I cannot simplify that radical. Awesome. Well, then that should be enough to get you going, and good luck.